Hi everyone, welcome to the third lesson for topic 4.4 Newton's laws of motion. So starting from this lesson, we'll be applying all the content that you have learned in the previous lesson or in the previous topics to help us to solve the problems. Okay, so some skills that you will need to remember is those Suvac formula, so the one for constant acceleration. Then after that, in forces and equilibrium, we learn how to resolve the force, right? So resolving forces. Then after that, how to deal with friction. How do we calculate friction? Then after that, the last one is what we learned in the previous lesson, which is the Newton's second law of motion, which is the formula for F equals to ma, or net force equals to ma. All right, so these are the things that we will be using for when we try to solve the question today. All right, so yeah, you can see the learning outcome is just solve the problems which may be modeled as the motion of a particle moving horizontally or vertically. Okay, so I'll be splitting the parts for problem solving into three, so I'll discuss it further in the introduction part. All right, so let's start the lesson. All right, so this is to give you a rough idea on what is the type of question that you are going to encounter here. Okay, so I kind of like categorize them into three general part. So the first one that we have is the horizontal and vertical motion. Okay, so this is also the first type of situation that we discussed in the first lesson for this topic as well. So basically, it's just like, horizontal motion, like you drive a car, you try to pull something on a horizontal surface, stuff like that. Then vertical motion, you drop something or you try to throw something upwards, then it falling down, so things like that. Okay. But now the situation that we will be looking at is the forces that involve is not in one dimension only. So which means you will need to resolve your force. Then after that, there's friction involved. Okay. Then after that, the second one that we'll be looking at is those the motion is in slanted plane. Okay, so yeah, you have how many degree from the horizontal surface and so on. Okay, and the last one is all the stuff that we have learned in our previous forces and equilibrium, which is about all the connected particles. So where we discuss about the tension, we discuss about the pulley. So yeah, then maybe we are going to look at stuff like lift as well. Okay, so this is how our lesson is going to be arranged as well. So today we'll be doing a horizontal and vertical motion. Then after that, slanted plane. So for connected particles, I might split it into two because there's quite a lot that involve here. Okay. So yeah, that's the idea. All right, so let's try to look at the first situation here, which is what we are going to do today, the horizontal and vertical motion. All right, so a quick recap on friction. So we know that a contact force between two surfaces can always be represented by two components, which is the first one is the normal component. So what we look at in the previous lesson as well. So the normal reaction force. So the force that acted on the object from the surface. Okay. Then after that, the second part we have the frictional component. All right, so we know that the normal component, right, will be always perpendicular to the surface. The frictional component will be always parallel to the surface and is always opposes the direction of which the object moving towards. Okay, so please remember it's not opposes the direction where your force apply. So it's the direction where the object move. Okay, so yeah, opposing the direction of motion basically. Okay, so friction can take and value up to a limiting value, so that's why we have what we call as the situation as limiting equilibrium, right? Okay, so for I mean at that moment where the friction has its maximum value is called as the limiting friction, which the F limit is equal to mu r. Okay, which mu is the coefficient of friction, then r is the normal contact force, which is the normal component that we mentioned previously. Okay, So when the object is accelerating, so this is the main focus of our lesson, right? Because in forces and equilibrium, we have learned how to deal with the situation which the object is at rest, is moving with constant velocity, or is in equilibrium or limiting equilibrium. Okay, so yeah, when the object is accelerating, we know that the push or the pull is more than the friction. Okay, then that's net force occurs. So that's why with the net force, then according to Newton's second law of motion, then we have acceleration, then only the object is accelerating. Okay, so yeah, must remember that at this point, right, so even the push or the pull is more than the friction, but the friction can only take the value up to the limiting friction only. So this is like the maximum of the friction. Yeah, but then due to the push and the pull is more than the friction, so that's why you have net force. And that's the case that we are going to look at today. Okay, so some tips here. While we try to solve the question, it's important for us to identify whether the force that we try to apply here, is it a continuous one or is it a instantaneous one? Okay, so let me try to give you a simple example on this. For example, if let's say there's a heavy trolley and we are trying to pull it, right? So the force that you are going to apply, it should be a continuous effort within a certain period, right? So this is like a continuous force. So which means at that period, your force that you try to apply will be a constant. But for instantaneous one, for example, when you try to hit a ball by using a bat or you try to kick the ball, so when you try to release the force, it's just at that instant only. Then after that, there's no continuous effort over there, right? So that's why it's going to give you a different situation where you try to look at these two different idea here. Okay, so you will actually understand it better when we move on to the example. So I hope that you can keep this in mind. All right. So some of the things that you will be continuing using will be the Subat formula here for all the constant acceleration case that we have. Then other skills that I'm not going to do any recap here is like the resolving forces. I hope that you still remember, right? It's like either the force cos theta or force sine theta. Then, of course, the previous lesson, the Newton's second law of motion, F equals to ma, or net force equals to ma. All right, so now let's try to move into the example. So this is a simple one as warm up. Yeah, so yeah, example one, there's a box of mass 25 kg is dragged along a smooth surface. Okay, so when I try to look at the word smooth surface here, which means there's no friction involved. Okay, so it's dragged along a smooth surface by a force of 30 Newton acting at 20 degree above the horizontal. So which means that's a horizontal smooth surface. So this is a box of a mass of 25 kg. So which means the weight will be 250 lah. Alright, then after that is dragged along a moved surface by a force of 30 Newton. So if let's say this is our horizontal, then which means it's going to be like this, then 30 Newton. So 20 degree above the horizontal. Okay, so the question one is to find the acceleration and the normal contact force. So the normal contact force will be perpendicular to the surface, right? So that's why it's here. So this is the normal contact force. Okay, so if we want to find the acceleration, so which means we will need to apply our Newton's second law of motion here, which is the F equals to ma. So the only force that, because since there's no friction, right? So that's why the only force that we have is the forces for the drag. So which means the force will be equal to ma. Okay, so the force here, when we try to resolve it, then this is how we can get 30 cos 20. So I hope that you still remember how to do this because this line is touching the angle, right? So that's why cos. So 30 cos 20 will be equal to the mass here is 25 kg and we want to find the acceleration. So just by using your calculator, then you will be getting 1.13 meter per second square. Okay, it's pretty simple. So now the normal contact force, so which means we will need to resolve it to the vertical component. So must remember, so please remember that in this case, your R is not equal to W only, right? Because you still have your 30 here. Okay, so that's why when we try to resolve it, so going up, we have the component for the normal contact force and then plus 30. sine 20, and it will be equal to the force going down, which is the weight, which is 250. Okay, so the resultant force will be just equal to 250 minus 30 sine 20, and this is going to give us 240 Newton in 3SF. Okay, so as simple as that. So now let's move on to example 2. Okay, number 2, part A. A curling player tries to slide a curling stone of mass 20 kg along a horizontal ice rink to stop on top of a target which is 46 meters away from where it was released. Okay, so let's try to make a simple diagram here. So which means there's a horizontal ice rink. Okay, then we have this curling stone which is 20 kg, so which means it creates a weight of 200 Newton. So to stop on the target, so which means, for example, if let's say this is a target, then the distance between the where it starts and the target is like 46 meters, right? Okay, so the coefficient of the friction between the force and the between the ice and the stone is 0.05. So which means we know that there is a friction involved here. So let's try to assume that the curling stone is released to this direction. So which means this is where the force is positive. So that's why we have the friction moving to opposing the direction of the motion, right? So we have this friction. Okay. So the player releases the stone with a speed of 6.5 meter per second. So which means at this point, the U is equal to 6.5. So find how far from the target it stops. Okay, so that's basically the question. So let's try to see whether there's other force that we didn't put in yet. Okay, so we have, so since that's weight, right, then it's motion involved. So that's why obviously we have the force from the surface to the object as well. So this is the normal reaction. Okay, so now this is a case where I want to discuss with you for the force. Okay, you see, the player releases the stone with the speed here. Okay, so you see, right, when you try to slide a curling stone, are you going to continuously apply the force on this curling stone? Or it's like just you try to hit it, then you try to release it, am I right? So this is like one-off hit, then after that, it will just, the stone is just going to continue to move on until it just stop lah, right? Okay, so in this case, right, which means what we are looking at is like it's an instantaneous force. So the force is not constant at all time. So that's why can we try to label our force over here? Am I going to put anything like pushing force here? We can't do that because if let's say we try to do that, which means it's going to be a continuous force already. If it's a continuous effort, right, then you'll realize that what the curling player can do is that he can continuously apply a certain force, then until a certain distance that he is confident that the stone is going to stop at the target, then only he release, right? But by reading from this question, you will understand that it's just by a hit, then the stone is released. Then after that, we want to check how far from the target the stone stops. Okay, so that's the idea. I hope that you can get it. So, okay, you might have a question where then what is the impact of the force that applied by this player? So that's why we have this situation which they say that the player releases the stone with a speed of 6.5 meter per second. Okay, why is that so? Because for this player, the push or the force that apply on the force, right, has its own of F equals to ma, and am I right? So that's why the question already did this for you, that the acceleration at that time actually caused the stone from at rest to the speed of 6.5. So that's why when we try to attempt this question, the initial velocity is 6.5 but not 0. So where is this impact come from? Is actually from the force that applied by the player. Okay, so that's why the situation that we are looking at here is after the force. So which means it's after the stone is released by the player and it's actually having a speed of 6.5 already. So that's why in this case, we are not going to include that in our force diagram. So we are going to look at now it has a velocity of 6.5. Then we have this friction. Then what is the motion after that? Okay, so I hope that you can get the rough idea. and hopefully to meet up some parts that I might miss it out in the previous lesson as well. Okay, so let's continue to solve the question. So yeah, we want to find how far from the target it stops, so which means we might need to find what is the displacement, right? So since we have the initial velocity, which is 6.5, and where it stops, meaning the final velocity is equal to 0, so which means that there are another two variables which we need to get, either acceleration or either the time. Okay, so yeah, in this case, then I think it's quite obvious that we need to get the acceleration, right? Since we have the force and we know the net force is only the friction. So for us to get friction, then F is equals to mu R. So that's why we can get our normal reaction force first. So in this case, you can see there's no other force that involved in the vertical component. So that's why our R is basically equal to our weight, which is equal to 200 Newton here. Okay, then after that, we can move on. So by looking at the motion as positive, so that's why the friction is in another direction. So negative F will be equal to ma. So the friction is mu R and equals to ma. So the mu here is 0.05. Okay, then the resultant force that we get is 200 and is equal to 20a. So from here, then I can get my acceleration is negative 0.5 meter per second square. So which is logic in this question because yeah, what happened here is that that's friction. So that's why what you expect is that the curling stone is actually slowing down, right? So the acceleration is negative. Okay, so now we have all the component already, and I think we can find our S. So let's try to write down the variable. So U is equal to 6.5. V is equal to 0 because until it stops, right? So A is equal to negative 0.5 and we want to get the S. So we can always use the formula of V squared equal to U squared plus 2AS. So let's substitute 0 is equal to 6.5 squared plus 2AS. Okay, so from here then you can solve the equation and we can get 42.25 meter. So we want to get the distance, right? So we know that the distance from where the stone is released and the target is given 46 meter. Okay, so that's why we are just going to use 46 to minus 42.25 and that gives us an answer for 3.75 meter. Okay, so yeah, just like that. So which means that the displacement, the total displacement for the movement from the release of the stone is 42.25. So that's why it's still having a distance of 3.75 from the target. Okay, so now let's look at part B. So in a game of curling, there were sweepers who sweep the ice to polish it and to reduce the coefficient of friction, which is the mu lah. Okay, assuming that they lower the coefficient equally along the entire path, find the reduced coefficient of frictions that required to get the stone to land on the target. Okay, so which means in this case, right, if let's say the coefficient of the friction is changed, so which means by using the same force, right, what happened is that by using the same force, then it will actually give you a larger acceleration. Because, okay, you can imagine coefficient of friction tell you how rough the surface is. So that's why when the coefficient of frictions is reduced, meaning now the surface is smoother. So when the surface is smoother and you try to apply the same force, then the acceleration will become higher, right? So that's the idea. So now for us to find out the coefficient of friction, then we need to do the opposite thing lah, which is we want to find out what is the acceleration for now. Okay, so for us to reach on the target first. So which means in this case, right, we have the same thing, the initial velocity is equal to 6.5. Then after that, the final velocity is 0 as well. But now the distance that it will land on the target, so that's why the displacement is going to be 46. Okay, and we want to find out what is the acceleration. So V squared is equal to U squared plus 2AS. So 0 equal to 6.5 square plus 2AS. Okay, so by solving this, then we can get A will be equal to negative 0.459 meter per second square. Okay, remember to keep this in your calculator, yeah, because this is like after rounding. Okay, so after we get this, so which means that we want to find the force, right? Then after that, only we can find the mu. So that's why the force negative friction is equal to MA. So negative mu R is equal to MA. So negative 0.05 I'm sorry, the 0.05 is what we want to find here. So negative mu, the resultant is still the same, which is 200. Okay, and it will be equal to 20, and our new acceleration that we need for the stone to reach on the target is negative 0.459. So from here, then we can get mu is equal to 0.0459. Okay, so when you try to check on this value with the previous one, so this one should be a number that's smaller than that. Like if you get something bigger, then you know that something wrong there already. Okay, so that's the part. Alright, so now let's move on to example 3. Alright, example 3. So this is a two stages question. So I think we can try to read through the whole question first before we move on to solve it. Okay, so a box of mass 10 kg is pushed from rest along a rough horizontal ground. So rough as if there's friction. Okay, so of size of 50 Newton for 3 seconds. So that's why it's a continuous push. Okay, it's not like an instantaneous like just now. Alright, so the coefficient of friction is 0.45. Find the speed where when it stops being pushed. So meaning for this situation, right, when we try to put in a force diagram, then it will be this box. Okay, so it has a weight of 100 Newton. So it's being pushed of a size of 50 Newton for 3 seconds. So it depends on you. So we can try to do like this. So each push for 50 Newton for 5 seconds. Okay, then after that, there's a friction opposing it. Then don't forget that we have this normal reaction force. Alright, then after that, you can see what happened for the second stage is that the box then slows down because of the friction. So it means that after the 3 seconds, the box is not being pushed anymore. So now there's only friction, right? So you can imagine that the acceleration will be negative now. So the second force diagram that we have here is going to be the same for the rest. I mean for the weight, okay, which is the just now what is it already, the 100 Newton there, right? Then after that, the normal reaction here, but then now the push is not there anymore, and we only have the force that opposing it, which is the friction. Okay, so that's the idea. So later while we are solving it, then you can see that we will have different acceleration because of there are different situation of forces involved. Okay, so now let's try to look at part A. Okay, so yeah, since we have the force diagram already, so I think we can move on to find out the speed. So which means that the initial velocity is actually 0 because it's pushed from rest, right? Then we want to get the final velocity, which is v. Then we also have the t here, which is 3. So which means that we need to get our acceleration from the force here as well. Okay, so how can we do that? So the net force is equal to ma. So since the direction of the motion is over this side, right? So we try to make going to the right as positive, and that's easier. So that's why we have the push minus the friction will be equal to ma. So the push is 50 Newton, the friction is mu r, and is equal to 10 for the mass. Then acceleration is what we want to find. So substitute our mu here is 0.45, and the resultant force here, there's no other force as well, right? So that's why the vertical component, you only have R and W. So that's why the R here is exactly the same with our weight. So 100, okay, then equal to 10A. So from here, then we can get 45, 50 is minus 45 is equal to 10A. So that's why the acceleration here is 0.5 meter per second squared. So after we get the acceleration, so you can see at this point, right, the force is actually still, I mean, the push is still larger than the friction, so that the acceleration is a positive number. So the initial velocity is 0. Final velocity is what we want to find. I'm sorry. So the acceleration is 0.5. and it's given that the force is applied for 3 seconds, right? So T is 3. Then the final velocity when it stops being pushed, so it's after the 3 second lah, 3 second it is pushed. So that's why we have this one, and we can use V equals to U plus AT. So U here is 0, A is 0.5, the T is 3. So from here then I can get the final velocity is 1.5 meter per second. Okay, so I hope that that's easy. Then after that, the box slows down because of the friction. Find the total distance the box has moved. So which means that we can try to find the first stage first, because just now we only have the time, the A, the U, and the V, right? We doesn't have the distance for the first stage where the push is applied. So that's why let's try to find out the first stage first before we find out the new acceleration. So which means let's try to use the information that we have. So the U is equal to 0, A is equal to 0.5, and T is 3. And now we want to find what is the displacement. Okay, so by using the formula of S equal to UT plus half AT square, and I can get 0 plus 1 over 2A 3 square. Okay, so from here 9 4.5 half, so 2.25. All right, so this is like the stage 1. Okay, so now let's try to look at the part where the box is slowed down. So when the box slows down, then which means, sorry, what I mean is that after 3 seconds, the box is not being pushed. So that's why the only force that exert on this box is the friction. So that's why it causes it to slow down. So that's why our net force here will be only equal to the negative friction. Okay, then equal to MA. So negative mu R, negative 0.45. Then the R is 100, then equal to 10A. So from here that I can get A will be equal to negative 4.5 meter per second square. Okay, so after I got this, then I can move on by using the same idea here to find out the distance for the second stage. So the initial velocity will be the final velocity for the first stage, right? Which what we get in the part A, which is 1.5. Then the new acceleration here is negative 4.5. Then the final velocity until it stops, so that's why 0. Then we want to find what is the S. Okay, so we can use V square equal to U square plus 2AS. Then we get 0 equal to 1.5 square plus 2 negative 4.5, and S is what we want to find. Okay, so from here we can have I think it's 9S, okay, then equal to 1.5, so 2.25. So our S2 here is going to be 0.25 meter. So the total distance will be equal to the first one plus the second one, which we have 2.25 and plus 0.5. So meaning after the push is not being applied, then it only moves for 0.25 meter. So the total distance that the box move is 2.5 meter. Okay, so I hope that that's okay. So basically, you need to understand that in what situation, what is the force that remain in the system. Then after that, you just use the different net force, then you have different acceleration, then continue to solve it. Okay, so now let's try to look at two past year question, then we'll end this lesson. Alright, example 4. So it's a past year question from question 2 paper 42 March 2020. It's a last year paper. Okay, so a particle P of mass 0.4 kg is on a rough horizontal floor. So rough, the mass here. So the coefficient of friction between P and the floor is mu. a force of magnitude 3 Newton is applied to P upwards at an angle of alpha above the horizontal. So where you are given tangent alpha is 3/4. So when you have this kind of question, it's important for you to know that since the force is not parallel to the surface, right? So that's why it's important for you to know that the normal reaction force, the R is not equal to your W anymore. Okay, so you might be very careful later. So the particle is initially at rest and accelerates at 2 meter per second square. Okay, so that's quite a lot of information. So let's draw the force diagram first. So that's a horizontal floor. Okay, so we have this particle P here with a mass of 0.4 kg. So the weight is 4 Newton. The coefficient of friction between P and the floor is mu, so that's okay. So a force is applied to P upwards at an angle of alpha. So that's why if let's say this is the horizontal line, so which means I have this force going up. Okay, so moving upwards, so it's 3 Newton. So at an angle of alpha, so this is alpha. Okay, then after that, the particle is initially at rest, so we know that u is equal to 0. It's a bit ugly, so yeah, u is equal to 0. Then after that, the acceleration is equal to 2. Okay, and the question tells us that tangent alpha is 3/4, so maybe you can try to find out the other as well. So if let's say this is my triangle, so this is the alpha, so tangent alpha is 3/4. So which means it's OA, right? So OA. So that's why from here I know this is 5 lah. Then I know that sine alpha is going to be 3/5 and cos alpha is going to be 4/5. Okay, you can just put in like all the information that you have here. So yeah, then other than that, let's put in some other force. Then you have friction over here, right? Then of course the normal reaction. Okay, so the question wants us to find the time it takes for P to travel a distance of 1.44 meter from its starting point. Okay, so which means that in this case we have, we have U, A, we have S, then we can find the T lah. So there's no force involved yet. So it's just a normal suvat. So U equals to 0, A equals to 2, and the S is 1.44, and now we want to find out the T. Okay, so S equal to UT plus half AT square. So S is 1.44, 0, half AT square. So that's why here then we have T square is equal to 1.44. So square root, then we have 1.2. Okay, so yeah, T must be greater than 0 lah. So that's why we only take the positive part. So T is 1.2 second. Alright, so after that, let's try to look at B. So the question wants us to find out the mu. Okay, so from here then, we know that the net force of this system is actually giving us acceleration of 2. So that's why we can try to use this idea to actually help us to solve that. Okay, so but in this case, perhaps we might need to find out the R first, because the R here is not only equals to 4. Yeah, that's is going to affected by the 3 Newton here as well. So that's why it will be easier when we try to find the R first. So let's resolve everything to the vertical component. So part B. Alright, so since it's a pool, so that's why it's going to be R plus 3 sine alpha. So R plus 3 sine alpha, it will be equal to the weight going down. Okay, so R plus 3, so sine alpha just now is 3/5, right? And then the weight that we got just now is 4. So by doing this, then we have R equals to 4 minus 50.61.8, so 2.2 Newton. Okay, so from here, then we can get our R is equal to 2.2 then now we can resolve in the horizontal direction, right? So remember, yeah, because there's a net force, so that's why please do not do in equilibrium like your left hand side and right hand side is the same. Okay, so yeah, make sure that it's like the net force is equal to ma. So that's why in this case, then it will be the net force equal to ma. So the net force here will be equal to the force that you have, then minus off your friction, right? Okay, so that's why in this case we have the force is 3 cos alpha. So it's going down, yeah, 3 cos alpha. Then after that minus the friction, then it will be equal to ma. So cos alpha just now we got 4 over 5. Then minus off the friction, mu is what we want to find, resultant force is what we got here, so 2.2. Then is equal to the mass is 0.4 in this question, and the acceleration is the part A acceleration which given from the question, so 2. Okay, so after we solve, then we can actually get 2.2 mu will be equal to move this over here, then we can get 0.8, 2.4 minus 0.8, so 1.6. Okay, so from here I can get mu is equal to 0.727. So remember that if let's say you get a mu in a negative number, then you must always check your answer because your mu is a coefficient of the friction. So that's why it's supposed to be a number that's like 0 point something, then until maybe 1. So if let's say you get a very big number or you get a negative number, so those are cases that you must check it again. Okay, so yeah, that's the idea for this question. So now let's try to look at the last one. Okay, number 5, a block of mass 3 kg is initially at rest on a rough horizontal plane. So the mass initially at rest is a rough, so that's friction. So a force of magnitude 6 Newton is applied to the block at an angle theta above the horizontal, where cos theta is equal to 24 over 25. So remember that there's an angle involved, so that's resolving, so that's why your R is not necessarily equals to W. Always remember this. So the force is applied for a period of 5 seconds. So during which time the block move a distance of 4.5 meter. So in this case, I think it's a bit similar with number 3. So that's why when you look at the question for the part 3, right, they'll ask that if let's say there's a force that remove, then after that, what happened to the block after that? Okay, so yeah, the pattern is like roughly the same, but I believe that in your exercise it should be quite easier because I actually take the harder questions so for our discussion, so it will be easier for you when you move on to the question. Okay, so now let's try to draw the force diagram for this question maybe. So we have this rough horizontal plane. So the block of mass 3 kg, so it gives us a weight of 30 Newton. Okay, so there's a force that applied to the block at the angle of theta as well. Alright, so yeah, then cos theta is equal to 24 over 25. So later we can solve that up. So this is a force of 6 Newton. So rough surface, so that's why we have the friction. So oops, I'm sorry, wrong direction. So it's a pull, so that's why the friction is moving over here. So we have the friction, then after that, blah, blah, blah. Okay, so t equals to 5. The initial velocity is 0, then the block moves for a distance for 4.5. Alright, then let's try to solve for the cos theta as well. So this is our triangle. So it doesn't matter what shape of triangle that you are drawing. If let's say you want to draw it like this, then at the end you still get the same answer one. Don't worry about that. So 24, 25. So Pythagoras, then you should get 7. So from here, then you can we do not need tangent, right? So cos is 24 over 25. So that's why sine theta will be equal to O than H. Okay, so yeah, I'll always encourage you to actually put your answer in this form rather than to find shift cos than to find the angle, because if you want to do like that, then you remember to store your value in your calculator lah, to avoid the mistake in terms of the rounding error. So that's why this is a much more accurate approach to go with. Alright, so yeah, the question wants to find out the magnitude of the frictional force on the block. Okay, so I will always suggest you to finish reading the whole question first because you see, right, when you try to look at number one, they ask you for the magnitude for frictional force. Then number two, they ask you for the coefficient of friction. So you can roughly imagine that in your part one, right, while you are solving it, you shouldn't do anything about your mu r yet because that's the part that come in for your part two. So that's why this can give you an idea how you should go with the question. All right. Then after that, you need to find the magnitude of the frictional force, then show the coefficient of the friction. It's basically to find your mu lah. Then after that, the last one is after the distance of 4.5, then the force is removed, then you need to find the total time. Okay, so now when we go back to 1, so we know that we should not use F equal to mu r in this case. So how are we going to do that is that by using the T, U, S, then which means we can find one more variable that we want, right? Is it like whether you want to find your V or whether you want to find your A? So in this term, we can actually find our A. So after we get our A, then multiply with the mass, then we can get the net force, right? So from the net force, then we can get our frictional force. Okay, so I hope that you can get the idea. So now let's move on to the working. So yeah, since we already written everything here, then we are not going to repeat that anymore. So basically, we want to find what is our acceleration. So UTSA, so we can use S equal to UT plus half AT square. Okay, so from here, then we have 4.5 is equal to 0 plus half A 5 square. So 12.58 is equal to 4.5. So from here we can get the acceleration is equal to 0.36 meter per second square. Okay, so after we got this, then now we can move on to the force. So the net force is actually equal to MA, right? So that's why the net force in this question, then it will be your 6 cos theta, then minus off the friction, which is what you want to find, then equal to the mass is 3 kg, acceleration is 0.36 as what we found just now. So from here, then we can solve it already. So 6 cos is 24 over 25 minus F equal to 1.08. So we can get our F is equal to 4.68 Newton. Okay, so yeah, by doing that, we solve our 1. So now go to number 2. We want to show the coefficient of friction is equal to 0.165. So in this question, again, so you have the degree here. So that's why the forces that, the normal reaction force is here. Okay, so the R here is not equal to W only. You need to resolve the 6 sine theta as well. So that's why number 2, let's try to do the resolving part first. Okay, so all right, this one. So I just want to clarify that. Please remember that in this case, why can we do that? The going up and going down is the same, which means it's equilibrium for the vertical component. It's because of this block is going to move along the horizontal line. So that's why, since the resultant force occurs for the horizontal component only, so that's why your vertical component should give you a resultant of 0. If your vertical component did not give you a resultant for 0, then what happened is that the motion will be like going up like that already. You get what I mean, right? So that's why for this case, for all the questions that we attempt for this particular lesson, so everything that you will see is like the block is pushed and it's like along this thing. So that's why the motion is only the horizontal motion or even like the vertical motion. So that's why when it's a horizontal motion, then which means that the vertical part should be in equilibrium, then the resultant should be 0, because if not, the resultant cannot be in the horizontal movement. Okay, so right, so now let's try to look at this. So part 2, show the coefficient of the friction. So let's try to find our R first in this case. Okay, so we have R plus 6 sine theta should be equal to the weight. Okay, so let's try to solve it. So R is equal to our weight here is 30 and then minus 6. So sine theta just now is 7 over 25. Okay, so from here then we can solve our normal reaction force is 22.32 Newton. So please remember for this number you cannot round it off because by using your calculator then this is an exact value. So which means after 32 there's no decimal place anymore. So that's why you shouldn't round it off for exact value. Okay, then after that now we have our resultant force already. So the friction, okay, will be equal to 4.68, right, by using our what the answer that we get in part 1. So as y mu r is equal to 4.68. So by using calculator and you will be able to get 0.165. If you didn't get this, then you must check because the question already tell you that the coefficient is 0.165. Okay, so now let's try to move on to 3. Sorry, let me try to see how much space I have. Okay, all right, so number 3, when the block has moved a distance of 4.5 meter, the force of magnitude 6 Newton is removed, so the block then decelerates to rest. So find the total time of which the block is in motion. Okay, so which means now it's the same thing like number 3 just now. So what happened here is the block, you'll be only left with the force for the, okay, let me try to do it here maybe. So which means that for the block now, we have only the force that is the friction. Okay, so which means now there's no 6 Newton anymore. So this is what remains in the system. All right, then we want to find the total time for the block is in motion, right? So I think for the first one, it already gives us that it's 5 seconds. So that's why we do not need to find the first stage. So now we need to move on to the second stage. So since we doesn't have the initial velocity, so that's why we need to find the final velocity from the first stage first. Then only we can move on, right? If not, then we can't do anything. Okay, so which means for here, then we can try to do number 3. Okay, so this is for the first stage where it starts from rest. Then after that, the total distance is 4.5, right? Then we have our acceleration is equal to 0.36. So we want to find our v. Okay, so v square is equal to u square plus 2as. So 0 plus 2as. So from here, we can get our v will be equal to 1.8 meter per second. So you want to find the v here because this final velocity is our initial velocity for our second stage, which the force of 6 Newton is removed now. Okay, so we need to get our new acceleration first. So in this case, then what we left with is negative f equal to ma. Okay, so that's why negative. Yeah, make sure that you do not use this because this is a friction where the 6 Newton is still there. So that's why you need to calculate your new F here, which is by using the mu and also multiply the resultant here. So the resultant here, since there's no 6 Newton anymore, so the resultant here is basically equal to the weight lah. Okay, so the weight here is 30, so that's why 30 and then equal to the mass 3 then A. Okay, so by solving this, then we will be able to get the acceleration is equal to negative 1.65 meter per second square. So which is logical answer because your acceleration should be a negative one since there's only friction, so it should be slowing down. Okay, so after we got this, then now we can proceed with finding the time for the second stage. So the initial velocity is 1.8, the final velocity is 0, then we know that the acceleration is negative 1.65. So from here, then we can find the time. So v is equal to u plus at. So 0, 1.8 plus negative 1.65, then t. Okay, so by solving this, then we can get t is equal to 1, then 1 over 11s. So for the first stage, we know that the force is applied for 5 seconds, right? So that's why the total will be equal to 5 plus 1 over 11. So you can get your answer 6.09 second in 3SF. Okay, so I hope that you have a good idea on this question. So yeah, then I think that you shouldn't have any problem when you move on to the past year exercise because these are the questions that having higher marks. So I try to get them in for the discussion here. All right, so spend some time in doing your questions. So that's it for today's session. Thank you.